let's look at the two-port network. The two-port network has two pair of nodes, and each pair of nodes you have a current and voltage, and there is one constraint on this. The returning current here has to be I1, as the returning current here has to be the opposite. This current here had to be opposite to the I2s. Okay, so that's the kind of the how we can tell this the two-port network or not. If you have four nodes or two pair of nodes that do not follow this constraint, meet this constraint, and in that case, that's not a two-port network. But in our discussion, we don't really have much. We are not going into the detailed characterization of a two-port network. The way the text present is not most common way of characterizing the two-port network. But in any case, so for two-port network, let's see, we have the voltage and current, and so the input the independent variable could be voltage or current for V1 and I sub 1, and the output or the response could be current and voltage, depending on what are the quantity you are most interested in your system, right? And so it could be current or voltage. So let's see, there are four different types of network functions. In this case, we call the transfer functions. And so in this case, if we have the output is the voltage and the input is V1, and so in this case, the V1 it would be a voltage source independent variable, and we can find we define the voltage transfer function as the ratio between the output and input. And the current transfer function, similarly, if the input is the current source I sub 1s, in that case the I2s and over I sub 1s. Okay, and also we have a transfer impedance, and transfer impedance is going to be equal V2 s over I1s. So it's still kind of V equal I times Z, but in this case, the V2 is the response, the output voltage, and you have the input current. So this is the ratio we call the transfer impedance, because these are on the two different sides, right? And for we also have a transfer admittance, and in this case, the transfer admittance of the I2 would be the output, and V1 would be the input. And V1 would be, so in this case, V1 is independent variable. And in this case, I1 is independent variable, is independent. And in this case, I1 is independent as well. And the transfer admittance is the V1 is independent. Okay, so how you find these transfer functions, right? Or the four different types. Most of the time, you will be able to find using the series and the parallel and voltage division, current division, and the things like that. And if you have op amps, remember operational amplifier. If you have op amps, you need to recognize the whether they're inverting, non-inverting, right? So let's recall what the op amps. Remember the op amps we have is non-inverting terminal, inverting terminal, and for op amp to operate as amplifier, we always have feedback connected to the inverting amplifier, the inverting terminal, the minus sign here, right? So this minus sign plus sign is not really related to the the voltage reference marks. Okay, just make sure you don't get confused. So this is the basically indicating the inverting terminal or non-inverting terminals. So the first one here, the configuration in this case, this is we call the inverting amplifier, because and in this case V2 and V1 they are related to, and this one I don't want to memorize this, and if you want to memorize it's fine, but it will take, it will disappear or you're gonna forget sometimes, right? So the simple way of figuring this out is using the virtual open circuit, virtual short circuit, and virtual open circuit as well. So virtual open circuit, that means the current going into the non-inverting terminal and the inverting terminal are both 0 amps, right? The voltage across these two terminals is 0. So based on that, we can see the current here. So the voltage here therefore is 0, right? Because this is reference node, so this is 0. So because the voltage across it is 0, so therefore the voltage across at this node here is 0 volts. So therefore the current here is let's see, the I1 as, let's see, the I2 as, so I1s is going to be equal V1s over Z sub 1s, right? And I2s is equal V sub 2s over Z sub 2s. So therefore, we know at this node here, because the current here is, this current is 0. So if these two elements are essentially connected in series, right? Although we have the third element, the op-amp, the inverting terminal connected to this node as well, but since that current is 0, so therefore you can do the KCL at that node there. So I1s is equal negative I2s, right? So entering current should be equal to leaving current, or so therefore you have V1s over Z1s is equal V2s over Z sub 2s. So therefore negative here, right? So therefore we have V2 over V1s. So in this case, I'm gonna divide both sides by V1, right? And I need to multiply both sides by Z sub 2. So I got a Z2, Z sub 2 over Z sub 1s. And don't forget about this negative sign. The reason we call the inverting amplifier, because we inverted the polarity of the input, right? So we have the negative sign here. And also, if you, as I did for in the Google Colab notes, and you could also use the voltage division. Right? This voltage division in this case is kind of not really straightforward, right? But I think it's still you can do the voltage division if you want. So let's see the voltage division. If we, since this one here, this is 0 current, right? So these two elements are connected in series. So I can do the voltage division. The voltage across this one here is just equal negative V1, right? So negative V1s is equal to the impedance Z sub 1s over Z sub 1s over plus Z sub 2s times V2s times the V2 minus V sub 1s, right? So in this case, I can do, let me see if I can figure that out. So let's see, yeah, so in this case, I can multiply this out. I can move this to the other side. I got Z1s over Z1 s plus z sub 2s minus 1, right, times v sub 1s. So I basically I multiply this times this and move the other side, move to the left side. So therefore this negative sign is gone, and I got a z1 s over z1 plus z2 and times v2s, right? So in this case, what I got here is on the left side, let me move this slightly lower. So in this case, I got on the left side, I got negative z sub 2s over z sub 1s plus z sub 2s, right, times v sub 1s. That's equal z sub 1s over z sub 1s plus z sub 2s and times v sub 2s. So now I can cancel the I can cancel the denominator because they're the same. So I reach the same conclusion, I think, right? So in this case, I got v2s over v sub 1s equal negative z sub 2 over z sub 1s. So this takes a little bit longer time, takes a little bit more effort, but you get the same result, right? And I hope you don't memorize this. And if you you want to find this one here, this easier case, you just take v1 over divided by that equal negative v2 divided by z sub 2. You can start with that. That's the two ways of getting this. And for I'm gonna keep the example later. So let's look at the non-inverting. So this is a non-inverting amplifier, and in this case, this is actually so in this case if we try to find v2 over v1, in this case we have 0 voltage here, right, and we have 0 current here. So therefore this node voltage here, this is v1s. So this one actually the voltage division is way easier compared to the other case. So based on the voltage division, so the voltage here across this is going to be equal to v1s, right? So therefore v1s, the total voltage across these two elements here is v1 is v1s, the total is v2s, right? Because the total here, this voltage with respect to the reference, all the reference nodes are the same. With this reference node here is v2, and with respect to this reference node of v2 here, also the v2. So in this case, v1s is just equal the z1 over z1 plus z2 and times the v2s. So this is based on the voltage division. And in this case, if we divided v1 on the both sides, right? So v1, v2 over v1, and in this case, and then we need to multiply the inverse of this. And in this case, we have that's going to be equal to z1 plus z2 divided by z sub 1s, right? Or alternatively, you can think about this. You divide v2 on both sides, and then you invert both sides, right? So that's either way will work. So in this case, we got a z1 plus z2 over z1. And in this case, we call it non-inverting because we don't really have a negative sign there, right? So that's for the basic the op-amps amplifier here. So we're gonna look at a couple of examples in the next video clip. Okay.